Actually a quick lesson on Newton's third law, which states that for every force there's an equal and opposite reaction force. The third law of motion, which is actually a little bit different than the second law, doesn't really have an equation that's associated with it. And you could put it into terms of an equation that force of 2 acting on 1 is equal to negative force of 1 acting on 2. But we don't need to worry about that at this point. We just need to understand the concepts behind Newton's third law. It's very, very important to study the third law because we really want to understand and place it in context with the rest of dynamics, because it's going to help us to create certain connections a little bit later on. So let's take a look at a few action-reaction pairs. So forces that occur in action and reaction pairs. So walking, here we have, I guess, Mickey Mouse, who's walking backwards. So this is the force that you would produce on the ground, or the force that Mickey would produce on the ground, or whoever it is. And of course, the force that you're creating acts in the opposite direction to what the ground produces on you, right? So the force that you give to the ground and the force that the ground gives to you are equal and opposite. Here's an apple that's on a branch, okay? Gravity is, of course, pulling that apple down, but the stem, which is attached to the branch, is keeping the apple up. So these are equal and opposite action-reaction pairs. In swimming, the force of your arm of course pushes backwards, but you swim forward, and that's because the water creates an equal and opposite force on you. So you may push the water backwards, your arms push the water backwards, but the water pushes you forward. And so that would be an action-reaction pair. Sometimes in firing a rifle, right, you press a trigger, and there's some kind of explosion which sends the bullet out. But of course, what does that do? It recoils backwards, and of course that explosion basically pushes the gun backwards, and so those are equal and opposite reaction forces. Sometimes if you're on skates and you're up against the boards and you push on the boards with your skates, of course you push in one direction on the boards, but the boards push back on you, and so you end up moving backwards. And when a space shuttle lifts off, the thrust of the engines and all the gas that's being burned and all the fuel produces a thrust downwards, but of course the air pushes up on all that gas, which is what forces the shuttle up into the air. And so maybe you're asking, if action forces cause equal and opposite reaction forces, why don't all forces just cancel out? And why does anything happen at all? And so you may have ideas about that. And certainly the students in my class have ideas about that. And so just think about that. Why does anything happen? And of course the answer lies in the fact that that's true, of course, for a pair of action and reaction forces. But really, we should look at free body diagrams for each object. Okay, so from those before, let's consider an example of someone on skates or a hockey player pushing against the boards. And so we'll draw a free body diagram for the player, and then later we'll draw a free body diagram for the boards. So here is the player who is on skates, and so we want to say, okay, well, what forces are acting? Well, the ground is pushing up and gravity is pushing down. And of course, this player is pushing on the boards, but that isn't what's acting on the player. What's acting on the player is that the boards are pushing back on the individual, on the hockey player. And of course, this is why the player moves in the direction of that force. Right? There's probably also friction acting in one direction, but it certainly wouldn't be as big as the boards. So now let's draw our free body diagram for the boards. Here, the player pushes on the boards, so there's an equal and opposite reaction force. The force of the boards and the force of the push are the same. And then there's the force of the ground, which in this case is much larger than the force of the push. For the boards, the forces are all balanced and there's no motion because the boards aren't going anywhere just because somebody pushes on them. But for the player, the push from the boards is the only external force. It's the only external force that really has any size that matters, because ice produces a very low friction environment. Right? The same wouldn't be true if we were talking about, say, someone pushing against a wall in their shoes. But because we're on ice, the friction is so small, right, that the only external force of any consequence is that reaction force of pushing on the boards. So the player moves backwards. What this means is that action-reaction forces never cancel out because they act on different objects. And when we're talking about free body diagrams, we're only talking about the forces that act on one individual. So here's an example. A student sits on a chair with another student pressing down on her shoulders. Draw free body diagrams for the person in the chair, the chair, and the ground. And then for each free body diagram, list on the diagram and explain what's happening. Okay, so here we go. Here's a free body diagram. This is for the person that's sitting on the chair. So what forces are acting? Well, there's someone pushing down on her shoulders. So that's F push. There's also gravity that's pulling this student down, this individual student. And what's keeping her from falling? Well, the force of the chair is pushing her up. Okay, so now what's acting on the chair? Because we need to draw a free body diagram for the chair as well. Well, what's pushing down on the chair? We got gravity, yep. So the gravity that's acting on the chair is pushing down. What else is pushing down on the chair? The student from above. Okay. And of course, why is the chair not falling? Well, because it's supported by the ground. So we got the force of the ground as well. And then here's the ground. And the ground is, of course, basically feeling the force of the chair, the force of the legs of the chair. But why is the ground not falling? Well, because it's being supported by the school. And you can insert whatever school acronym you have, whereas ours is KCI. Yours might be something different. And so what we want to say is, okay, well, what are the action-reaction pairs then? What's acting? What are the action-reaction pairs? Because they do exist here. Okay. So between the student and the chair, there's a set of action-reaction pairs, and then between the chair and the ground, there's an action-reaction pair. So between the student and the chair, basically what happens is that the student presses down on the chair, and the chair presses up on the student. So this F chair that's acting on the student, that's going to be one half of it. And of course, what's pushing down on the chair? Well, F student. And so there's an action-reaction pair. They have the same magnitude, but they're in opposite directions. What about for the chair and the ground? This one's a little bit simpler because it's got to be F legs, because the legs of the chair are pushing down on the ground, and the ground is pushing up on the chair. So the action-reaction pair here is F ground equals minus F legs of chair. They're the same, they're just in opposite directions. So those are action-reaction pairs and Newton's third law.